The idea of continuity can help us evaluate limits of our function. So a function is continuous at a number a if and only if that limit as x approaches a of our function is exactly equal to f of a. So the idea being, if I have a function that's continuous, which could look something like this, if I'm evaluating the limit at as x approaches a, our function's continuous if it's just equal to that output. So I'd have this coordinate a f of a. So in those scenarios where we were evaluating the limit laws in the previous videos, could have been we were starting with something that was not continuous, like these scenarios where we would have holes in the graph. But what we could do is morph it into a continuous function so that we could evaluate by plugging in. So a continuous function is, in terms of graphing, a continuous function is something we could graph with never lifting our pencil. So what I drew up here was continuous because I put my pencil down and then I was just making waves and I can continue on. But as soon as I would have to pick up my pencil to draw a next part, that would make it discontinuous. So some scenarios we're going to see is when we have asymptotes. Another scenario would be if we had a hole in the graph, so I'd have to pick up my pen to make the hole in the graph. Some different cases there. So graphically, when we think of a function as continuous, if it is unbroken, in other words, you could draw the entire function without picking up your pencil. What are three subproperties of what makes a continuous function is, our first one is that f of a is defined so that we have that coordinate. Also that the limit as x approaches a from both sides for that function exists, so they're approaching that same coordinate. And then that the limit as x approaches a of our function is equal to that output value. So that all occurs at this coordinate here where we have the coordinate, that two-sided limit exists, and that limit is just going to be our function output at that point. But if any of those breaks, it means that the function is not continuous, it's discontinuous. So with that, what we're going to do is talk about the types of discontinuities we can see come up. So we want to draw sketches for each of these cases. So let's talk about the case where 1 and 3 fail. So this would be the idea that 2 is holding true, the two-sided limit exists, but the coordinate is not defined, and that two-sided limit is not equal to just our function output. So what that's going to look like is that's going to be when we have a hole in the graph. So if I was graphing something and we had a hole, this would be a case where f of a is not defined. If this is our coordinate a right here, it's undefined at a. Also, that two-sided limit is not equal to f of a because f of a does not exist here. But we do have the two-sided limit. It's approaching this value that would be where that hole is located. This is called a removable discontinuity. So removable discontinuity happens when there is a hole in the graph. Let's see what happens. What if only 2 and 3 fail? So what this would look like is we do have f of a, but the two-sided limit does not exist, and the two-sided limit is not equal to just our function output. So what this could look like is wherever a is, we're defined there, but the two-sided limit does not exist. What that could look like is we are defined in one spot, but for the two-sided limit to not exist, we need to jump elsewhere and maybe do something like this. So we're defined, the two-sided limit does not exist, which also means that two-sided limit, there's this property, so if 1 or 2 fails, 3 is going to fail as well. It just implies it. So with this is called a jump discontinuity. And so with both of these cases, if we were drawing these, we'd have to pick up our pencil while we're graphing. We'd have to pick up to draw that hole and then continue on. Or with the jump, we'd be drawing, and then we'd have to pick up our pen to continue drawing on the other side. So these are discontinuities. Let's look at the case where only 3 fails. So we're going to have a case where f of a is defined. We're going to have the two-sided limit exist, but that two-sided limit is not equal to our function output. So what that would look like is going to look like our removable discontinuity up above, because that was a case where we have our two-sided limit. But now if we want to be defined at that point, what we're going to do is define elsewhere. So this is also called a removable discontinuity. So what we have with this one is the two-sided limit exists. We're approaching the hole in the graph. F of a is defined because we have a defined coordinate at a. However, that third property fails because that two-sided limit is different from the y-coordinate of our defined value. Okay, there are going to be 2 cases where all 3 properties fail. So we're going to have f of a is undefined, the two-sided limit does not exist, and that's going to force the third one to fail as well. So let's look at the 2 cases here. For one of them, what I'm going to do is go back to the jump discontinuity, but what if we weren't defined at a? So what that would look like is, let's say a is right here, and I have part of my function, but we're going to be undefined there, and then undefined up there as well. So with this, all 3 properties fail because at a, our function is not defined. We don't have a coordinate. That two-sided limit does not exist because of that jump, and that all makes property 3 fail as well. So this is just another form of our jump discontinuity. Another scenario that we have that would make this true, where at a, if our function is not defined and the two-sided limit does not exist, that can happen with our vertical asymptotes. Let's say we had a vertical asymptote at a, and my function does something like this. We go to negative infinity on one side, and then for the two-sided limit to not exist, I have to go to positive infinity on the other side. So our function is not defined at a, the two-sided limit does not exist, and that all makes property 3 fail as well. This is called an infinite discontinuity. So these are the types of scenarios that can make a discontinuity in our graph, and we want to be careful of these when we're evaluating our limits, because we prefer, if we have nice continuous functions, we can just do that direct substitution like we were doing with our limits in the previous. Or if we have these scenarios, maybe we can adjust our function so that it becomes continuous so that we can evaluate limits more easily.